Well, I think let's get started. It's 3:04, so rolling, we're rolling. Okay. So it's my great pleasure to introduce Pedro DiNezio, who is visiting us virtually from Colorado. I think he's there. Can't tell from the background. I'll give a little background on Pedro. So Pedro was a student here from 2008 to 2011. He was also employed across the street at AOML, so he had the really unique distinction of crossing the Atlantic several times on XBT cruises while he was writing tons of papers for his PhD thesis, which then won the Smith Prize for best PhD thesis that year. He then, after leaving Miami, he went on to Hawaii, where he was a postdoc and scholar there for a couple years. He spent some time at Boulder as a Roland Madden visitor there as a fellow. After that, he went to Texas, UT Austin, where he spent 4 years there as a research scientist at the Institute for Geophysics there, a research institute. And since 2020, he's been an associate professor in the Department of Atmosphere and Ocean Sciences at CU Boulder, which is a really great place to be. I will add that he has former undergrads and former grad students from Rasmus working with him. And so we're confident that he's going to set up Rasmus West out there. So if any of you want to go visit, we have our second home at the foothills of the Rocky Mountains there in Boulder. You're going to hear about his work. We've had a whole interesting discussion that has been happening on email with Sankey and some other folks at AOML, about 10 or so people who are just happen to be discussing this topic. And Sankey brought up Pedro's paper, and then now here he is to explain it all to us. So I could brag about Pedro in many ways. I counted the number of publications that he has on his CV, which is really astounding. He's published in areas from paleoclimate to future climate change and El Nino prediction. He's boldly made some predictions about La Nina. He has gotten tons of NSF and NOAA grants. So if you want to know how to write successful grants, you can also ask Pedro that question. He's enormously successful in that. Done great science with lots of different people. His CV has some of the top people in our field as co-authors, and everybody loves working with Pedro, but not as much as I do. So I'll stop there and turn it over to Pedro. I will, before you get going, Pedro, I just want to housekeeping, make sure that everybody knows that we'll have a Q&A session at the end where Roland asks that when you can ask a question, let me know, but we want you to unmute yourself and turn on your video so you can ask the question in person. If you're not comfortable with that, put the question in the chat and I'll read it. We have had lots of interesting chats go on with these Compass seminars, so feel free to go ahead and chat on the side. But when it comes to Q&A, we're going to want to bring those up and record them. So take it away, Pedro.
Awesome. Thanks for inviting me. It's great timing because I've been wanting to talk about some new studies that I've been doing. I feel like it's been 10 years I've been working on these things, and there's still unanswered questions, but hey, El Nino is the most important mode of climate variability in the planet. So we want to know what we'll do in the future. So here I have another bold prediction. I forgot about that La Nina of 2017, but you'll see I'm going to attempt a bold prediction. Here, the different thing is that I'll try to validate, right? When you do a prediction, you need to verify, and predicting future changes are really hard. I mean, how do you verify a prediction for the future and the greenhouse warming? So paleoclimate allows you to do that, but you have to be really careful when you look at the mechanisms and the valuation. So I hope I convince you that this is a prediction of what could happen in the future in the tropics. Of course, it's contingent on anthropogenic emissions. If we curtail emissions, then this prediction will not happen. But if we stay in a business as usual scenario, this could be an outcome. And I feel pretty confident about it. So tropical variability can cause extreme climate events. I just want to point out one here. In 2016, in April of 2016, Southeast Asia experienced record-breaking temperatures. You can see them in the map as the temperature anomalies for that month. This is not a heat wave because it happened over a month, but you can think of it as a heat wave. Some places exceeding 10 degrees. It led to all sorts of records broken in places like Thailand or Vietnam, particularly power consumption. April is the hottest month of the year in Southeast Asia. So it was even hotter. And in this paper with Kausab Tirumalai, we show that extreme temperatures in April in Southeast Asia are correlated with El Nino. 2016 was right after the last record-breaking El Nino, or close to record-breaking El Nino, depending how you measure it. And you can here nicely see the temperature anomalies from multiple data sets average over Southeast Asia and the Niño 3.4 index in wintertime, and how nicely the spikes correlate with El Nino events. But on top of it, we have the long-term warming. So the two combined produce these extreme temperature anomalies over that month in Thailand. We think El Nino could be coming stronger. If you look at the Niño 3.4 index, the sea surface temperature anomalies averaged over the central equatorial Pacific. There's an intriguing trend over, say, the last 60 years towards more extreme El Nino events, although we had some record-breaking El Nino events in the late 19th century. So we don't know if this increase in extreme El Nino, these really strong events, 82, 97, and 2015, was caused by anthropogenic warming, or are just part of the really strong natural fluctuations in ENSO variability. So if we want to understand if El Nino changes, we can go back to Bjerknes' seminal paper. He has this map that I really like that shows the temperature departures from the zonal mean. So with really limited observations, he identified the cold zones in all tropical oceans. So you can see that these are the places that are on the zonal mean colder. The Eastern Pacific and the Eastern Atlantic and the Indian Ocean more uniformly warm, and there's no departures from that zonal mean. So he had the intuition, when you read the paper, that those gradients are what give rise to variability. And he came up with a Bjerknes feedback, which we have refined over the years, but that Bjerknes feedback depends on the direction of the prevailing winds, which are driven by these underlying temperature gradients. So the Pacific and the Atlantic have trade winds blowing from east to west, and the Indian Ocean has weak westerlies. And now we understand a bit more how these things work. The direction of the wind sets up the thermal structure of the upper ocean. So here I'm showing the analysis data. I'm still not showing model simulations. So these are just annual mean ocean temperatures in all three tropical oceans. I'm centering on the Pacific. So the Atlantic to the right, the Indian Ocean to the left. And you can see that the Atlantic and the Pacific have a thermocline, the interface that separates the warm waters on the surface with the cold abyssal waters below, that is tilted from east to west. So it's pretty shallow in the east. And again, these are the annual mean conditions average over the last 50 years on the equator. And the Indian Ocean has a thermocline that is rather uniform across that basin. And it's the position of the thermocline and the direction of the prevailing winds that set up these feedbacks. And that's why we have variability in the Pacific, strong tropical variability in the Pacific and the Atlantic, and not in the Indian Ocean. So this will be my contemporary version of the Bjerknes feedback. If the trade winds relax, then the zonal currents will weaken. So the equatorial, the south equatorial current will weaken. and the thermocline will deepen in the Eastern Pacific. Both will act to expand the warm pool. So when the zonal currents weaken, the warm pool expands because these equatorial currents are pushing warm water towards the west, and the cold zone warms up. So the Central and the Eastern Pacific warm up, and then the trade winds relax and further, and the zonal currents, and this is how you close this positive feedback loop that Bjerknes had the intuition gave rise to El Nino in the Pacific, and also thought that it explained why the Atlantic has variability and the Indian Ocean has a lot more muted variability. So you can see that, and again, I'm showing observations for now. You can see the standard deviation of sea surface temperature anomalies, so computed as departures from the monthly mean seasonal cycle. So the standard deviation gives you a metric of how variable these sea surface temperatures anomalies are, which are dominated by interannual timescales. So in the Pacific, we see high variability associated with El Nino. We see the Atlantic El Nino here, not so strong. And in the Indian Ocean, we see the signature of the Indian Ocean dipole with some variability in the eastern side of the coast of Sumatra and Java and of the coast of East Africa. But the Indian Ocean doesn't have a large-scale mode of variability like the Pacific and the Atlantic. So how will this tropical variability change with global warming? People have been asking this question forever. I mean, I tried to answer this question in my PhD. I think I understood some things, but if we use Bjerknes' just intuition, then we know that the gradients are expected to change. And there's a lot of debate if we are seeing these changes, but if we trust the models, and this is what the models predict, under greenhouse warming, the Eastern Pacific will warm up more than the warm pool, and that will represent a reduction of those gradients. So here I'm showing the warming predicted by a set of CMIP3 models. So these models are pretty old. This actually is a figure adapted from one of my papers from my dissertation. But if you do the same thing from CMIP5 or CMIP6, the latest coordinated experiment of future predictions, you'll get the same results. Models have consistently predicted these patterns in which the cold zone will warm up more under increasing greenhouse gases than the rest of the tropics. And you can see here by this stronger warming, right where the cold zone is. And then in the Indian Ocean, you see a bit of the opposite. Actually, the western side warms more, and the western side is slightly less warm today. The Indian Ocean today is like this bathtub of just warm water, but it's slightly less warm in the west. And the models predict that the west will warm up more. So it's a bit of the same prediction than the Pacific, like colder areas, or the areas that today are relatively cold are warming up more than the areas that are relatively warmer. So in a nutshell, models predict a weaker gradient in the Pacific, a stronger gradient in the Indian Ocean. So if we just follow Bjerknes' thinking, we should expect stronger variability in the Indian Ocean and weaker variability in the Pacific. If a stronger gradient gives rise to modes of variability, and a weaker gradient should weaken those modes. But we know that these predictions are not true. So for the Indian Ocean, actually, Bjerknes' intuition somewhat works. Here I'm showing for CMIP5, so you can believe me that CMIP5 models do the same thing. The pattern of warming to the left with surface wind stress changes after year 2050. And again, this is a multi-model mean, so it's the average of all models, and under the high emission scenario RCP 8.5. So what you see is that everywhere warms, but the eastern side of the Indian Ocean warms less. And together with it, we have changes in winds that follow those gradients, those anomalous gradients. And when we look at the changes in variability in all the models averaged together, we see an increase in the standard deviation of the sea surface temperature anomalies after the year 2050. And again, this is the average picture of all models. You can see that the changes are not large, up to 0.1. It's really small. But this is because the models actually simulate a wide range of changes in variability. We could plot each individual model, the changes in the winds and in the x-axis. So you'll see negative values because that's the change in wind stress. So this means that the change is easterly. So those weak westerlies that the Indian Ocean has in the current climate could weaken, maybe become zero and become weakly easterly. And what we see is a huge range of changes in the direction of those easterly winds. And in the y-axis, we have the changes in the standard deviation over the eastern Indian Ocean, where that blob of increased variability occurs in the ensemble mean. One thing to note is that this is not the Indian Ocean dipole, because the Indian Ocean dipole has a center of action off the equator, off the coast of Sumatra and Indian Ocean in the eastern Indian Ocean. So this looks like a different thing. And there's a huge range of variability. If some of these models are right, 0.5 increase in the standard deviation of sea surface temperature anomalies is a huge increase. If you recall, the Pacific today reaches in some places 1.2. So this is a massive increase in variability. And according to the models, depends on the strength of the changes in the winds, which is reasonable. Is the winds become, those westerly winds that the Indian Ocean has become more easterly, then eventually they will set up upwelling and they will show the thermocline, and then we'll start having these interactions between the ocean and the atmosphere that will give rise to sea surface temperature variability. So how do we validate this? What's going on here? Well, we can look at past climate changes. So we can see which of these outcomes is possible. And one target is the last glacial maximum. The reason why we look at the last glacial maximum is because this is 20,000 years before present. Our planet was covered by massive ice sheets over Canada and Scandinavia and the southern tip of South America. Even Antarctica was bigger, CO2 was lower. And the reason why we look at this past climate to test some of our ideas of how the climate system works is because it's quite well sampled. We had a lot of paleoclimate estimates of what the climate was and what the variability was. And it's also quite well dated. We can use radiocarbon ages to precisely date different intervals. And the climate changes were large everywhere, including the tropics. It's a case of global cooling, partly due to reduced greenhouse gases, but also because of the presence of these massive ice sheets. So it's not truly an inverse analog to future global warming, but of all the climate changes that we have available to test our theories, I would argue that is the one that provides us with a big climate change and also lots of data. And the one thing to consider also for the LGM is that there was a 120-meter drop in sea level that exposed the changed coastlines and exposed shelves. You can see them in this map, particularly these shelves in the maritime continent, the Sunda and the Sahul shelf. I've done a lot of research on how the exposure of those shelves changes the climate of the tropics during glacial intervals. And we're going to use those ideas to see what happens to the Indian Ocean during the last glacial maximum. So the LGM is another case of a stronger gradient and stronger variability. So it works also according to Bjerknes' hypothesis. To the left, I'm showing a map of sea surface temperature changes. So now you'll see that everything shows cooling because this is a globally colder climate. But we also see patterns that resemble, and here I'm showing the annual mean conditions. The shading is from a simulation that I ran when I was at NCAR in 2014. So it's a simulation of the climate of the LGM. We apply all the boundary conditions, the reduced greenhouse gases, the ice sheets, the changing coastlines and exposed shelves. And what we got is that cooling everywhere because the reduced greenhouse gases and the cooling effect of the ice sheets. But we also found this altered gradient in the Indian Ocean that you can see in the shading. The eastern side in the simulation cooled a lot more than the western side, almost as in the global warming simulations, in which the eastern side warms less than the western side. So we see a change in the gradient in the same direction. In this simulation, the change in the gradient is not driven by greenhouse gases. It's driven by the exposure of those shelves. The Sunda shelf here that you can see, and I plotted the coastlines, the continents following the LGM coastlines. And also there's a shell here that is not showing up in the map. There's a whole shell connecting New Guinea and Australia. And both of them affect in the simulation, the water circulation in a way that drives these anomalous winds that you can see in the plot with also an easterly direction in the changes in the wind. And actually in this simulation, these changes are so large that the Indian Ocean develops a climatology very much like the Pacific, with absolute easterlies and upwelling in the eastern side, which you can see here, cooling the eastern side. And each one of the circles is estimates of sea surface temperatures from the LGM. So these are actual measurements in the same units. And you can see that there's not a lot of estimates, but on average, the proxies on the eastern side show more cooling than the ones on the western side. There's probably a difference in the absolute magnitude. Overall, the proxies don't show that much cooling like in the model. And that's a completely different topic that you might be interested because we think that current models cannot explain the magnitude of cooling at the LGM, but they seem to explain these patterns. More cooling in the east, less cooling in the west. And in our simulation, we match that, and we can also see the changes in the wind. None of this is surprising. This is what you expect from equatorial dynamics. And in the model, we can also look at the variability. So same thing, we computed the standard deviation of, in this case, we converted temperature and salinity into the equivalent isotopic composition of oxygen. The isotopic composition of oxygen that then will be captured by forams, and this will become clear in the next slide. The reason why we did that is because we're going to compare the model exactly with measurements from paleoclimate data. But we converted temperature and salinity variability into these delta 18O measurements, quantities, and then we computed the changes in variability as a percentage. And you can see also a massive increase in variability in the eastern side of the Indian Ocean. Again, not surprising. As the climate changes, the thermocline shoals in the eastern side of the Indian Ocean, upwelling is also established, and those allow stronger Earth interactions, increasing the variability there. So I had this prediction from this model, and this goes back almost to when I was in Hawaii, and I was talking to Feifei Jin, and he told me, yeah, if the mean climate change, the variability should change, but how do you test this? So I team up with Kaustubh Tirumala. He was a postdoc in my team when I was at UT. Now he's an assistant professor at the University of Arizona. And he has this technique that can estimate past variability. So how does he do it? I'm going to walk you through the steps. There you see Kaustubh looking at the microscope. So you can get sediments from an ocean core. Take two horizons, one for current conditions at the top, one deeper for the LGM, and then wash the sediments and pick these bugs. These are foraminifera. These foraminifera live for a month. And when they build their shells, these bugs build their shells with calcium carbonate. When they build those carbonates, they use oxygen of different isotopic composition based on the temperature of water. So if you measure the isotopic composition, the ratios of the isotopic composition in these shells, you will get a snapshot of what the temperature was back in the last glacial maximum. So Kausab looks at the microscope, picks a ton of these bugs, up to 100. It's a lot of work. So we had this hypothesis that the Indian Ocean had to have experienced a lot of variability back in the LGM. So imagine all the measurements that we did. We took, I'm going to go back to the previous slides to show you, he took, applied that technique for these 4 sites that you see in the Eastern Indian Ocean. 1, 2, 3, 4. 3 in the center of action of the variability and 1 outside for a null hypothesis. So we hope to see increased variability here and weak changes or no changes in this side of the center of action. So made all the measurements. I remember when we were doing this, and it was quite another bold prediction, quite nerve-wracking. It's just every week he would get a subset of measurements from one of these sites, and one by one, they agreed with the predictions. So again, here you have another case of trying to make a prediction and then how you test it. So we got the samples, he measured, he picked the forams and measured the isotopic composition and these ratios, delta EDNO in each one of these bugs, both for current conditions and both for the LGM. And here you can see them plotted for each location going south. In red, the current conditions during the late Holocene, and in blue, the LGM. So we're plotting, we're removing the mean so we can focus on the variability. Each dot is an individual measurement from a foram. The isotopic composition of this delta EDNO measurement is inversely correlated with temperature. So negative values indicate warm anomalies and positive values indicate cold anomalies. And you can see in these box plots, which show the interquartile range in the boxes, you can see a massive, again, a massive increase in variability consistent with the simulations. And actually, we compare them apples to apples, converting the model output into the same quantities, and they even match in amplitude. With the 3 sites close to the equator, with a lot with much higher variability, and the other side showing no changes. So what drives this variability? Part of it is an increased seasonality. When the easterly winds develop, they create an annual cycle, a cold tongue, a tiny cold tongue in the Indian Ocean with an annual cycle, just like the Pacific. But we also wonder how the increased variability increase on interannual timescales. So we did these additional simulations in which we took our LGM simulation and we killed El Nino and the Indian Ocean dipole. So you can do that by restoring sea surface temperatures in the center of actions of those modes to climatology, to the climatology of the model. So in every time step, the model will be pushed to the seasonal cycle at that site, and El Nino will not be able to happen, and the Indian Ocean dipole, which is generated from this region off of the equator in the southeastern Indian Ocean, will also be able to happen. So if you did this in a simulation of modern climate, you'll probably get rid of, you actually get rid of all of tropical variability because you're killing 2 of the modes. You're still leaving the Atlantic El Nino. We did not kill the Atlantic El Nino, but assuming it doesn't play a role. And we tested this. We ran a controlled simulation, and when we did this, there was no variability. So we did the same thing for our LGM simulation, and we find that there was still variability. So the increase in variability does not come from El Nino or the Indian Ocean. It comes from something else. So we looked at that variability in our LGM simulation. So here I'm not showing any changes. I'm just showing the variability in this simulation of the last glacial maximum without El Nino or an Indian Ocean dipole. And we found this variability with a precursor. And the precursor was in the western side of the Indian Ocean. The precursor had a westerly wind direction, and the contours are showing variations in the depth of the thermocline associated with that precursor. So this also doesn't sound surprising, as the oceanic response to a westerly wind anomaly, which looks like a Kelvin wave, because these are positive contours, so indicate a deepening of the thermocline. So we composite all these precursor events, and this is how they look. There's a ton of them. These simulations were run for multiple centuries to make sure we had good statistics. And 3 months later, you have the peak of these events, which looks very much like an Indian Ocean, El Nino, with warming. And again, these are not changes. These are just anomalies in this simulation. So there's warming in the eastern side of the Indian Ocean. Focus on the equator. If you notice these sea surface temperature anomalies, which is a composite, so it's the average of all the events, they are all on the equator, and they are not here because in that box of the equator, we restore the SST. So by construction, this simulation doesn't have variability. And then other things you see in these anomalies is westerly winds blowing over the underlying, or driven by that underlying temperature gradient. So as the Eastern Indian Ocean warms up, the winds relax and become more westerly. So we have these westerly wind anomalies at the peak of these events. And also in contours, you can see thermocline depth anomalies, which are also quite canonical, with the response associated with Kelvin waves to the east, deepening the thermocline. And to the west, we also see the signature of the Rossby waves that we expect from equatorial theory. So this mode, which we call an equatorial mode of variability, we don't want to call it an Indian Ocean El Nino, or something else. Every time you name something related to El Nino, it doesn't work. But this looks exactly like the Pacific El Nino. A fluctuation in the winds in the western side of the basin triggers a Kelvin wave, or a set of Kelvin waves. When they reach the eastern side of the basin, they deepen the thermocline. That suppresses upwelling. We have to remember that in this climate, the Indian Ocean has climatological upwelling and shallow thermocline in the east, very much like the Pacific. So none of this is surprising. I mean, it's just a nice confirmation of equatorial theory that also works in the Indian Ocean if we alter the climate. And then we see evidence of the Bjerknes feedback amplifying these anomalies at the peak of the events. You may be wondering how this thing oscillates. It's really interesting. I'm not going to show it, but you can also look in the simulations how this El Nino could lead to a subsequent La Nina. And it actually doesn't, because the Indian Ocean is too narrow, and there's not enough time to trigger a La Nina in the next year, like in the Pacific. But I won't be talking about that. I also want to show that you can do the same thing for global warming simulations under the RCP 8.5 scenario. We did not perform a simulation in which we've killed El Nino and the Indian Ocean dipole. We just look at all the simulations in the semi-5 archive and composited the events based on the precursor. So we look at all those precursors in the Western Indian Ocean and composited them in all the simulations and in all the events in a bunch of simulations. And I'll tell you which simulations we looked. Actually, we looked only in the ones that showed increased variability. So you can see the same thing. In CIMIC 5, this precursor looks more like changes in the monsoon. And actually, this is quite interesting. I won't be talking about this, but they still have westerly winds that project on the westerly direction on the equator. And when we look at the contours, which are the anomalous depth of the thermocline, we also see a deeper thermocline. Mean that these winds trigger a Kelvin wave, and this is an average of a lot of events because we're looking at multiple simulations now, and multiple events in each one of these. And then you can look 3 months later and see what happens if these precursors lead to an Indian Ocean El Nino, and indeed they do. We see similar things like in our simulation, although now we're not restoring SSTs off the coast of Sumatra, so these anomalies expand away from the equator, but it looks very much like what we saw in that LGM simulation. With warming and weaker trade winds, which these are not trade winds, but westerly winds and a deeper thermocline, all reinforcing each other, sustaining these sea surface temperature anomalies. So if we go back to that scatter plot that I showed you, the dots, the models in blue, circled in red, are the models in which we see an activation of this El Nino, and are the models that show the strongest variability. And this red dot is our LGM simulation. So what we see is that we need large changes in the mean climate to activate this mode. The changes in the mean climate are shown here by the changes in the strength of the winds along the equator. Although this is somewhat troubling because you also have a range of changes in the winds that leads to the activation of the mode. This is something we're looking into. What is producing this range of outcomes in all these different models? But on average, we see that the changes in the mean climate have to be large. So the emergence of that anomalous of the gradients in the Indian Ocean due to greenhouse warming have to be relatively large, and as Bjerknes expected, that will give rise to the emergence of an El Nino-like mode in the Indian Ocean. So all this works really nice, exactly like Bjerknes expected it. This is, I like to think that the Indian Ocean works exactly like we think the Pacific should work, but the Pacific doesn't work that way. So I'm gonna walk you through, I'm looking at my time, I'm gonna walk you through how the Pacific Ocean works. So if the gradient weakens in the Pacific Ocean, then El Nino should become weaker. But if you look at CIMIC 5 models under high emission scenarios, and you look at the changes in the standard deviation on the Nino 3.4 index, a measure of the average amplitude of El Nino and La Nina, you'll see a lot of disagreement among models. So this is a bunch of models that participated in CIMIC 5, and you see that the Nino 3.4, the strength of ENSO measured that way increases or decreases. So is El Nino sensitive to external forcings? So you can test the same idea by looking at the past. And a really popular interval for looking at changes in El Nino has been the Holocene, because in the Holocene, insolation changed the annual cycle of the Colton, and that could have driven big changes in El Nino. So we wanted to test some of these ideas, is which intervals in the geological past that we have available paleo reconstructions of El Nino could be useful to find mechanisms that could help us connect past with future. So I took CSM1 and I ran it now not for the LGM, I ran it for multiple climate intervals every 3,000 years going back in time. So here I'm showing you intervals during the Holocene, 9, 6, and 3,000 years before present. And I'm plotting the amplitude of ENSO measured by the standard deviation of the wintertime Nino 3.4 index. So this is not a change. I'm just showing the amplitude of ENSO measured by this metric in the model. I'm plotting these values as distributions because we know that ENSO is highly variable. So these simulations are quite long, they're equilibrated, of course, and they're each one 500 years long. So these distributions that I'm showing as the box plots are the distributions of the 30-year values, because we have coral records of an average length of 30 years, just to get an idea of how variable our estimates of this quantity would be if we compare it with corals. And what you can see is that there's a weak trend towards an increasing El Nino, but it's also very variable. If you look at different 30-year intervals, you could have, you could probably find a different trend in the opposite direction if you pick these high values here and the lower values in this simulation. So we kept running simulations. We went all the way back to the LGM because we had that one. There's evidence from paleoclimate data that ENSO was weakened back then. So I'll talk to you more about that. And then we also run simulations in between. So what we found is that ENSO, at least in this model, can be highly variable. And this is a really good model. It simulates asymmetries between El Nino and La Nina. It's a model that I use for those predictions of the La Nina of 2017. And I feel pretty confident that it has quite an accurate representation of the dynamics of El Nino. And we also run a simulation for the future under CO2 doubling. And you can see that in this model, ENSO can change a lot. So I'm going to walk you through the results. What we found is that if we plot the distributions of the Nino 3.4 index, all the changes are in the worm tail of the Nino 3.4 index. And actually, the strength of ENSO as a whole is controlled by the number of extremes. So each circle here is one of these simulations. So in the simulations where ENSO strengthens, it's because there's more extreme events. Actually, these are events larger than 2 degrees Celsius. So under greenhouse gas warming, in this simulation, there's 1 out of 2 events and an extreme El Nino. And there's no extreme El Nino under those glacial intervals. So it happens that we have estimates of what ENSO did in the past, particularly from the LGM. And I'm going to walk you through this figure. It has a lot of information. So this is our latest figure for this paper that we're working on with Kaustav. The shading on the back is the changes in standard deviation simulated by the model. We're plotting the total changes because with this technique of these single bugs that I described before, we cannot distinguish what is controlled by ENSO and what is controlled by seasonality. But the stippling indicates where seasonality dominates in the model. So everything that is not stipple, it's where interannual variability dominates. And these are not measurements that Kaustav made. These are existing estimates of past ENSO variability made by other authors from multiple sites. So we only focus on those ones that are sensitive, where those sites are strictly sensitive to changes in El Nino. And the most important one is this site 849, because it's in the center of action of the Pacific El Nino. So you can do the same thing, plot the distributions from the forums and from the model. And you can see these box plots, like I show for the Indian Ocean. For the Eastern Indian Ocean, we have actual temperature measurements done in each forum. That is really expensive to do because you have to do it with a laser. So in that paper by Ford and others that I mentioned from Science, they did that. They measure a ton of forums with a laser to get the magnesium-calcium ratios that then you can convert into temperature. And they found a massive increase in variability, late Holocene to LGM. And our model does the same, probably not to the same extent, but you have to keep in mind that there's still a lot of variability in these intervals. There's a lot of internal variability. So it's possible that the proxies were capturing a period of much lower variability. But we did the math, and these changes that we see in the proxies cannot be explained without the force changes that we have in the simulation. We can keep walking along all these sides, but it will take me a while. So I want to show you this other side. This side is off of the coast of Costa Rica, and it's forams that live below the surface. So these forams can see the Kelvin waves, the coastal Kelvin waves that El Niño events trigger. And it's pretty clever to look at variability there. And the measurements were done with isotopes, not with temperature. But you see the same thing. The distribution of delta ET for the model conditions is much higher than for the LGM, very much like in the model. In the model, we also converted the output into the same quantities. And I could walk you through all the sides, and all the sides show weaker El Niño at the LGM. The western side should work the opposite way, because El Niño drives cold SST anomalies there. And there's this side that captures thermocline variations, but all of them show weakened ENSO. So how does this work? These are all the slides that I shared with everyone through that email, but we found that the Bjerknes feedback changes a lot between these simulations. It's really strong under CO2 doubling and almost zero under LGM conditions. We look at the Bjerknes feedback as a growth rate, as a function of seasons. So we focus in late summer when El Niño events grow. And that quantity, average over June and September to September, is correlated to the amplitude of El Niño events in the simulation. So the stronger the feedback, the stronger the amplitude of El Niño events. So how does this work? Which aspects of the Bjerknes feedback is being altered here? So there's a lot of things I can change. Is the coupling between winds and SSTs. So if the winds are more responsive to SSTs, the Bjerknes feedback will increase. There's this coupling that no one pays attention to, but we looked into it just to be rigorous, and it's the coupling between winds and the ocean. And it's controlled by the depth of the mixed layer. When the mixed layer is shallow, ocean currents and the thermocline are really responsive to winds. If the mixed layer gets deeper, that doesn't happen. And then the ocean thermal coupling, which depends on temperature gradients. So I'm going to show you which one explains the changes in the Bjerknes feedback, and this is my last figure. So the same figure that I show from the simulations for all the intervals past to future, and you can see the effect of each of those couplings on the total feedback. So on the y-axis, I'm plotting the strength of the Bjerknes feedback for all the couplings changing, and then if we are only changing one coupling at a time. And you can see that the changes are explained by that mechanical coupling, which is quite unexpected. So how responsive the ocean is to winds is what is controlling how strong the overall feedback gets, or how weak. And for this, the mixed layer is, the depth of the mixed layer is key. So ultimately, everything is tied to the strength of the trade winds and the Walker circulation. If we look at all these intervals, we see that in the intervals where the Walker circulation is stronger, the mixed layer is deeper. And the intervals that the Walker circulation is weaker, the mixed layer is shallower. And I'm plotting the strength of the mixed layer as the strength of the trade wind. So more negative values means more stronger trade winds. So the way we think about this is, this is my final slide. The gradients are not the whole story for the Pacific. Actually, what matters for the Pacific is the depth of the mixed layer. When we have a really deep mixed layer, like in glacial climates, when an El Niño event is growing, the ocean is not super responsive to those wind anomalies that trigger El Niño. And it's really hard to trigger extreme El Niños. Like, you could have a wind fluctuation, a westerly wind burst, an extratropical precursor that will want to trigger an El Niño event, but the ocean will not respond because the mixed layer is so thick that it's hard to move, and it's hard to get the Bjerknes feedback to be strong enough to trigger an extreme El Niño event. And the opposite happens in these simulations under future warming. The mixed layer becomes shallower for multiple reasons. The stratification goes up, but also the trade winds in these simulations weaken. And the mixed layer in the Central Pacific is controlled by the strength of the trade winds too. So a much shallower mixed layer makes ocean currents and the thermocline a lot more responsive to fluctuations in the winds, and then extreme events or extreme El Nino are a lot easier to trigger. The one thing I wanted to clarify is that the growth of these events here is dominated by zonal advection and less so by fluctuations in the thermocline. So it's these expansions of the warm pool that under glacial climates are really hard to drive, and under warm, and in the future, according to the simulations, will happen more easily because zonal currents that control the extension of the warm pool will be more responsive. And that will favor the occurrence of extreme El Nino. So together, these results show that in the Indian Ocean, if the mean climate changes according to what models predict, we could see the activation of this El Nino like mode that is not active today. So it could emerge as soon as 2050, and you can imagine that could drive new hydrological extremes associated with its teleconnections. And it's supported by our study of the LGM, in which the mean climate change a bit of in the same direction. So we know that if the Indian Ocean climatology changes in that way, this mode should emerge. And for the Pacific, works in a different way. We found that the mixed layer is the control on El Nino. And in the LGM, proxies show much weaker ENSO and quite consistently around the Pacific. And what I didn't say is that there's some paleoclimate evidence that the thermocline was deeper during the LGM, adding to some evidence for this mechanism. And to some extent, this could happen in the future, but the opposite. If the mixed layer shoals, then a lot more extreme El Nino will be triggered. And you can imagine what happens if we have more extreme El Nino. And I'll stop that and take any questions.
Thank you so much, Pedro. I was busy taking notes, and there's just some stuff going on in the chat. So let me open it up to everyone. Go ahead and jump it. Okay, I see clapping. You can raise your hand, unmute yourself, put something in the chat.
How can I raise it? How can I raise it? I don't see it raised.
Someone wants to raise their hand, but you can just unmute yourself. Whoever that was.
Hey. Yeah, this is Sankey. Yeah, I have a quick question to you, Pedro.
One request. Can you turn on your, turn your camera on so we can see you?
I am very comfortable. Yeah, hey, Pedro, good to see you. Good to see everybody. I have a quick question for you. I really love your Science Advanced paper. Every time I look at it, I really like it. I have one question. So I look into some of the CIMI-5 model. When I look into the Indian Ocean variability, some people did the EOF analysis in the CIMI-5 model under the current CO2 condition, and they do see some like a El Nino like a feature. So which doesn't really happen in reality, but some couple model do have it. Have you?
That's a good question. Yeah, the models are slightly biased. That's a good question. The models are slightly biased, and they already have a modern climatology that probably has an altered gradient. So some of those models that I show probably are already showing some of these events. We see an increase, but there's models that don't. And so some of the models don't have those models. So we looked into that, and it's a great question. And in CIMIP6 models look even better, but we haven't looked into that. So if someone wants to look into CIMIP6, the CIMIP6 models improve the simulation of the climatology of the Indian Ocean by a lot. Mm-hmm. At least there's a bunch of better models. Mm-hmm. So one could test that idea. But yeah, some models are closer to that state in which the model emerges. So then it's easier to push them into that.
Okay.
But the other thing to keep in mind is that the Indian Ocean is changing much faster than models predict. Like if we see at observations, the changes in the gradient in the last 100 years are in the direction that the models predict and are on the upper bound.
It's already happening. Okay.
Yeah, it's gonna happen.
All right. Great, thanks.
No problem.
Renellis had a question.
Hello, Pedro. Nice to see you. Great talk.
Hi, Renelis. Thank you.
You had so many great results. I guess going back to the Indian Ocean part, I posted the question in the chat. I was just curious. You focus on El Nino because, I mean, everybody, it's like the Pacific Atlantic bias, the El Nino, La Nina bias. But I was just curious if some of the sources of the equatorial cold tongue variability that you were seeing were due to instability waves during cold years.
Well, it's a good question. The resolution that we use for the ocean has this very linear, unrealistic, awful tropical instability waves. It has some, but we haven't looked into those LGM simulations. We probably should have, right? Once you create those meridional fronts because you're changing the mean climate, they should be there. I didn't look, to be honest. There's so much to look in those simulations. So it is possible.
It's possible. I was wondering about the coarseness of the model, and you're right, like the TIWs can be very regular if the model's too coarse.
Yeah, they don't break at that oceanic resolution. So they don't produce a lot of mixing because there's just this. But I don't know what the effect would be. It'll probably act as a feedback, as a negative feedback, right? Producing a lot of mixing. But I'm sure there's going to be so much compensation between other errors. And so if you believe the proxies, they seem to suggest that the gradient was altered in the same direction. But yeah, I mean, you're right. And now I'm thinking is those tropical instability wave could cause, right, monthly variability captured by the forams.
Right.
Yeah. They probably have the time scale, sufficient time scale. Yeah.
Ooh, that complicates the picture.
But we see a massive increase in variability. You saw it in those bags. It's huge, which is not surprising because you go from no variability to a lot of it. That's a good question. I didn't think about that.
I was curious, you had that picture of the ENSO sensitive proxies versus seasonal cycle sensitive proxies. Can you explain how do you make that distinction?
Oh yeah, that's a good question. We are tweaking all that rationale. I'm writing that paper right now. It's based on what the authors argued and also based on our simulation. So the argument becomes a little circular, right? You're using your simulation to ignore data sets, but you saw that in the far eastern Pacific on the equator, there's really a beautiful reconstruction of past variability from the LGM to present. It's a paper by Tony Kutabas, which shows increased variability at the LGM, reduced variability at the mid-Holocene, and then back up towards the modern. But when we compare our simulations, in our simulations, we see exactly the same across the time slices. And in our simulations comes from the changes in this seasonal cycle with very little influence from El Nino.
Okay. I see.
So that's how we rule out those sites on the east.
Right.
The sites that are really unambiguous are on the western side and the Costa Rica side, because they're capturing just the Kelvin waves, and in the western side, there's no seasonal cycle. So almost everything you see is interannual variability.
Oh yeah, Renellis has a good idea that tropical instability waves, or I guess any of this could be pumping nutrients up, which might also appear as influence of proxies.
Yeah, you also have upwelling. So the Indian Ocean at the LGM was probably entirely different, and it probably sustained a lot more productivity. We don't see biological effects because when you do those single Foram measurements, you can do the same measurements of carbon isotopes. That will tell you if the nutrient supply would have changed. And we don't see a big effect from that. So we think most of the variability that we see in the isotopes comes from temperature. That's all in the 2019 paper.
Okay.
Yeah.
Lou Gramer has a question.
Hi, Lou. I'm reading the question. Do you want to ask it in person?
We can't hear you so well, Lou, but
Let me.
Second.
yeah, that's better.
Is that better?
Yep.
Okay. So forams are kind of a proxy for corals as well. So they're calcifiers. They actually so to light, available light. I'm wondering if there's, variability in sustained cloud cover, for example, could change seasonality and could change interannual variability in foram growth. So there's a lot of uncontrolled variables in using them as a proxy. So I was wondering how you guys control for that.
Yeah, so the technique has been used and calibrated with the core top. So usually the model conditions are compared with observations and they match observations. So when you compare oceanographic measurements and you convert them into delta 18, then the magnitude matches. So that, and again, you could still have compensation between all these processes. And that's why you may see a signal that looks like just the climatic effects. But you could also, it's a good question. You could ask yourself if at the LGM, everything changed so much that you don't know if we are seeing a climatic signal or a biological signal. So we are trying to test this. People have developed models of forams, how a foram behaves. So, but then you have to feed it with nutrients. So to do that, you have to run the simulation with all the biogeochemistry. So you can feed the forams, feed. And then you could start testing these ideas with these models of what forams do. So it can be done. We're thinking of doing it.
That sounds actually pretty interesting. I also wanted to put in a comment. I'm impressed by the sustained focus of your research since 2008, at least. That's quite
I consider myself the most unfocused person in the planet.
Apparently not, my friend.
But yeah, I don't know. I'm really excited about this last paper because I'm working with, Kaustav is a lot of fun to work with. He was a partner with me and we're having a lot of fun. I'm sure you can tell. And it's a difficult problem. No one knows what Nino does. And yeah, thank you, Lou. I don't know. I try to have fun. This is the one thing I learned from Amy. The most important thing I learned from Amy is to have fun.
Good. Well, we have a few more questions in the chat. I don't know if you are able to hang around.
I'm able to hang around. Yeah.
Sumi, are you still there?
I saw that one by Sumi. Yeah.
Yeah. Do you want to unmute yourself, Sumi, and video so you can ask?
So my actually laptop is somewhere else, and so I can't connect to the camera. But I was wondering about the signal of wind it was showing in Indian Ocean. It seems that it is supporting the monsoon strongly, like there is, and like that's why I was wondering how is the monsoon signal in this model run, and also
No, go ahead.
And also, like, that's why I was wondering if it is a strong Indian monsoon, it usually, like, the signals over the equatorial Pacific is a strong easterly, so it actually reduced the El Nino signal, but how it is connecting with the monsoon. So that will be nice to see. But it's a really great talk. Thanks.
Thank you. That's a good question, Sumi. In those LGM simulations, the monsoon winds become stronger. We wrote about that in a paper in 2018. The monsoon winds become stronger, but the Arabian Sea becomes so cold because there's all this cold air from the ice sheets coming up from Arabia. We call that ventilation, that even though the monsoon winds become stronger, the monsoon does not become rainier. So I don't think that precursor depends on having a stronger or weaker monsoon. It's probably always there. Monsoon variability creates it. I mean, we haven't looked into that, and I mean, it would be nice to think about it. If we see that, I mean, it should happen in modern climate. It's just not triggering El Nino events in the Indian Ocean because the mean oceanographic conditions don't favor them. So it does look, at least in the CIMIP models, it looks like a monsoon precursor, and it actually happens in the same season. It's the precursor is in May. It's actually, let me remember, it's April, May, June. That's when that wind precursor occurs in the simulations. It's around the time the monsoon happens. So yeah, you could even think that you could change the relationship between the monsoon and the tropical variability in the future, because now you're having all these new interactions in the future. I hope I answered your question.
Yeah, that's really, it sounds actually very reasonable, because many model means like with this kind of warming, actually they might not have a wind pattern, but just the moisture flux shows when Indian Ocean is warm, it is a strong monsoon, and it might be reversed because here Indian Ocean is cooling. So yeah, that sounds really reasonable. Nice.
Thank you.
Pedro, I can't let you off without asking you, what if the models are wrong and the real force signal is a La Nina like?
It just happens the other way around.
Oh, okay. So then,
Yeah.
then it's
Extreme El Nino should become less frequent because your mixed layer is thicker and deeper.
okay.
Yeah, so it should work. I mean, the future would be like the LGM.
Right.
So yeah, you're always back to the mean state, right? Like, I think it's the biggest, most important question to understand all these other responses. All depends on what the mean state does.
Okay. Good. Then we have more work to do because nobody seems to agree on that yet.
I think we will know in 10 years once there's enough greenhouse gas forcing. It'll emerge. I think we'll see.
Mary Beth has a couple side comments here about the utility of repeated CMIP experiments. You might, Mary Beth, you want to ask? Pedro's in a good position because he's been CMIP 3, 5, 6, seeing the whole, you know, how things have changed. So.
Yeah, so I was just, that was a great talk, thank you. So I was just saying to Amy that you had said that the CMIP 6 did a lot better with the Indian Ocean resolution to solve with the air-sea interaction and the feedback and everything. And Amy and I had talked, but you know, this is like a big question is like, are the improvements of the CMIP models worth it? Because it's a lot of money and time and people working on it. And like, are the marginal increases or improvements worth it? So what do you think?
That's a great question. I go through phases of gloom and doom and optimism. I'm currently riding an optimism wave. But I think models have improved a lot. The simulation of ENSO has improved massively. You cannot do those predictions of La Nina that I did without these models that have extremely realistic dynamics, like El Nino's coming out of nowhere, then leading to La Nina, and then La Nina hanging for multiple years. I think that is very important in a model if we want to simulate what El Nino does. If El Nino is an, I mean, we know El Nino is not an oscillation, but if your model has an El Nino that is an oscillation, then it may not have this realistic responses because it'll be governed by different feedback. So I think the progress has been painful, right? You think, oh, these models all look the same, but I don't think, you know, I think Ben Kierman said this, that it's all the models catch up with the good models. So you always have bad models, and in each loop, in each CMIP, you have, you know, and I think I'm optimistic now that I think there's improvements in the simulation of the mean state are important. We see them in the Indian Ocean. I think CMIP 6 is so much better in the Indian Ocean. I think we should be more concerned about the simulation of ENSO. I think sometimes during the tuning process, we should try to have some El Nino, but it's not always ideal. I think we should pay attention a bit more to that in the development. You know, it's painful. So I'm optimistic. I think it takes a lot of work. Maybe it's because I'm getting old and I'm like seeing that progress is slow. I'm becoming more conservative. I don't know what is it, but I think it's mind blowing. I remember when I met with Mark Kane. I don't know if people care about this, but I was a student and I was starting to work with CMIP 3, and he told me that CMIP models were going to be everything in a few years. And it's like, what is this guy saying? And he was right.
We're all
I know that I remember that.
Yep, we're all going to spend all our time and then resources running. And now we have to run large ensembles of CMIP models because we've learned that you can't just look at a few.
There might be some power in all these extremely repetitive. So again, I'm going through an optimistic phase, but you can also think why it's not useful. I think it's useful. I'm actually amazed by the improvement in the simulation of some climate. You know, these are equations solved on a computer, and sometimes they look like nature. So if that doesn't blow your mind, I don't know what would. That's my last.
Oh, that's a perfect note to end on. Okay. Quote. Did we get that recorded, Roland? That's a good tagline. All right, everybody.
All right.
Thanks again, Pedro. We got a lot of chat.
Inviting me.
Want to check it out. Everybody was so happy to see you. Come back, like Lou says, come back, visit us for real sometime.
Yeah, I'll let you know. I haven't been in Miami in a long time, but
it's much warmer here.
It's nice.
I know. Maybe in this, maybe in February.
Mary Beth is moving to Colorado. She got a job at Colorado State, CSU.
But I'll be in Fort Collins, but I know it's not too far away.
Oh, when are you moving?
Next summer.
Awesome. Congratulations.
Rasmus West.
Yeah.
We're taking over Colorado.
Stay in touch. All right. Thanks, everyone.
All right. Bye, everybody. Thank you.
You're around.
Okay. Bye.